To the channel, and this is the fourth lecture of the engineering thermodynamics series. As you can see, we will be discussing reversible and irreversible process and also quasi-static. So if we just go for a little revision, in the last video or lecture we have studied about system, right? So to define the state of the system, we need thermodynamic properties, and we have also studied about state. Let's say it's state 1 and it is state 2. Okay, so if there is a change of the state of the system from state 1 to the state 2, we have called this as process, right? Process means change in state. And what is state? It is the condition of the system which is dependent on the thermodynamic properties, right? If you remember, it is, let's say, P1, V1, T1, and it is P2, V2, and T2. All right, and one diagram that is called indicator diagram or PV diagram. Okay, P stands for pressure and V stands for volume in the x-axis, pressure in the y-axis. So let's say this is the state 1, and there are many states, and the final state, let's say these are some states, and let's say this is the final state. Okay, so if we connect these dots of all these states, we get a path. We'll use this concept. Okay, we'll use this, and it is called PV diagram or also called indicator diagram. Okay, indicator diagram. And today our process, we'll also study those processes, the flow, non-flow processes like adiabatic processes, polytropic process, constant volume, constant pressure process. All those processes we'll study in the upcoming videos, but today our process is mainly about the one is that is reversible process, and another one is irreversible. You can say the complete opposite. Okay, so let's go for today's topic. Before going to the reversible and irreversible, okay, we will be studying the thermodynamic equilibrium. So we have today I have written the statements, the definition before going for the lecture, because otherwise it will take much more time in explaining. See, so your thermodynamics equilibrium is nothing but when there is no change in the microscopic property, if the system is isolated from the surrounding. Your system is isolated because there is no exchange of heat and no exchange of what should I say, no exchange of mass and no exchange of heat, that is the energy. If there is, and the system is isolated and there is no change in the property of the system, then the system is called is said to be in thermodynamic equilibrium. Okay, so let's say this is a system and there is a certain pressure and temperature of the system, and this is the pressure and temperature. The same pressure and temperature is outside the system, that is in the surrounding. Okay, that is in the surrounding. So this situation is called thermodynamic equilibrium. For the system to be in thermodynamic equilibrium, there are some conditions. Okay, for the system to be in thermodynamic equilibrium, there are some conditions. First one is the mechanical equilibrium. Let's say you are applying force F1 or force F2. If F net F2 minus F1 or F1 minus F2 is 0, it means F1 is equal to F2, then the system is said to be in mechanical equilibrium. The conditions are, it has to be in mechanical equilibrium, it has to be in chemical equilibrium, we'll explain this, and it has to be in thermal equilibrium. Okay, it has to follow 3 equilibriums so that the entire thing should be in. See, we'll go through all this. Okay. So this topic is thermodynamic equilibrium. So it has three conditions. First one is mechanical equilibrium, then chemical equilibrium, and then it comes thermal equilibrium. Okay. So mechanical equilibrium is nothing but balancing of the forces, or there is the net force acting on the system and the surrounding is zero. We can also understand it by this way also. Let's say this is a system and there is a P in, means internal pressure, and the external pressure. Internal pressure and the external pressure means P in is equal to Px, or you can say delta P is equal to 0. Then it does mean that it is in mechanical equilibrium, the first condition of thermodynamic equilibrium. And if there is no reaction taking place within the system, or there is no concentration gradient of chemicals, let's say your system has gas 1 and there is gas 2, both have same concentration, then there will be no reaction. When there is no chemical reaction going on in the system between the chemicals or the gases, let's say, then it is said to be in chemical equilibrium, the second condition of thermodynamic equilibrium. Okay. And the last one is the thermal equilibrium. So see the temperature, let's say this is the system and there is uniform temperature, let's say T, all throughout the system. And also see the temperature not changing throughout the system, also in the surrounding, and also there is temperature T in the surrounding. Okay, so this condition where there is no change in temperature in the system and the surrounding, and also there is a uniformity of temperature in the system, that condition is called thermal equilibrium. Okay, so these three equilibrium, thermal equilibrium, chemical equilibrium, and mechanical equilibrium, if the system is satisfied with three conditions, then it is said to be in thermodynamic equilibrium. Okay, so next process that comes is the reversible process. So next is the reversible process, which is also called ideal process. Why it is called ideal, we'll see. A reversible process is the one in which it can be reversed in direction following the same path as that of the forward process. Okay, we'll understand you with the help of PV diagram without leaving any change in the system as well in the thermodynamics, as well in the surroundings. Sorry. So this is our PV diagram or indicator diagram. Let's say this is state 1. And after following so many states, this is the initial state. Okay, and there is state 2, which is called final state. And if we connect all these states, the curve we get is the path of the process. You can say, since there is a change of state from one state to another, so it is if we join all the line or all the dots, each of the dots represents different states as it finally reaches the final state. Okay, so each of these states are in thermodynamic equilibrium. The three conditions that we have understood, mechanical, chemical, and thermal, after satisfying all those three, all the systems, even the state 1 and state 2 are in thermodynamic equilibrium. Okay, so let's say your process happens from state 1 to the state 2. Let me take this green color, state 2, and it follows this path. Okay, it follows this path. Okay, and after reaching state 2, it follows the same path to reach the initial state as state 1. Okay, means from state 1 to state 2, it followed a path. Then from state 2 to state 1, it followed the same path and reached the actual or the original state 1. those kind of process that we can explain, that we are explaining with the help of PV diagram, is called reversible diagram. See, when it reverses in direction, it follows the same path as that of the forward process. The forward process is state 1 to 2 and the reverse process state 2 to 1 without leaving any change. Means in the system and surrounding there is no effect of it. Okay, so for example we can say elastic deformation of solid. You will study it in solid mechanics or strength of material subject. Okay, suppose there is this spring. Okay, you are pulling it from this to side, giving it a tension. Okay, so after releasing the force, it will come back to its original state. Let's say this is the original state. This is the original state. Then after pulling with, let's say, some forces, okay, let's say some forces F1 and F dash, let's say, it comes back to its original state. So this kind of deformations can be classified as reversible process. Okay, so a reversible process is directly related to the thermodynamic equilibrium. You can also say that, because since all these states are in thermodynamic equilibrium, see, so it is related with all the reversible processes related with what we can say is thermodynamic equilibrium. Okay, so its example is elastic deformation of solid, like we have discussed about the spring. Spring is a solid, right? Okay, so let's see some conditions that is needed for reversible process. There should not be any loss due to friction. It is highly efficient. Okay, next, so you're highly efficient. Okay, means it performs with 100% efficiency and all. It is ideal. When it's called ideal, it's not natural, it's not spontaneous, and it satisfies the law of conservation that you have studied since class 9. So as you have seen, there is no difference in the P external, P in, that is the mechanical equilibrium, and each state, you remember all the states. Okay, all the states are in thermodynamic equilibrium. Okay, means mechanical and chemical and thermal equilibrium, and it happens at slow rate, very slow rate. Okay, so all the reversible processes are not natural, they are ideal and hypothetical, means it's not in the real world. And next comes is the irreversible process, the opposite of it. Okay, so in this process, both systems surrounded does not return to its original state. Okay, and hence it is called spontaneous or natural. So the process occurs only in a definite direction and do not proceed in the opposite direction without the action of external effort. Okay, let's understand it using the PV diagram. Let's say this is state 1 and it goes to state 2, the final state, but while returning it's not following the path, and also it is not reaching the state 1. For example, plastic deformation of solid. He'll study in solid mechanics and strength of material solid. If a solid reaches into the plastic range of the stress strain diagram, it cannot recover to its original state. It has to be in the elastic region. Okay, so this is an example. For another example, let's say there is a tank of water. Let's say this is the first tank and there is another one below of it. So there is a water flow from tank 1 to tank 2, let's say state 1 to state 2, but to return to the state 2, return from the state 2 to state 1, we have to have some motor or a pump. So we have to do some external effort using the pump and all. Okay, without the action of the external effort using the pump and all, we cannot return the water from the below tank 2 to the up tank 1. So this is the another example of what we can say is for the reversible process. Okay, so obviously the reversible process is the natural process that we see in our daily life. So it is mainly due to friction between surface and the solid, and it is viscosity. We'll study this in fluid mechanics. It's the fluid. It means the friction between the fluid layers and lack of thermal equilibrium. You already understand by this term. And the example that we have talked about is the plastic deformation and this tank 1 and tank 2 example. Okay, so here these two example can be written. And now the quasi-static. Okay, quasi-static process. This is quasi means almost, and static means slow. Just remember this word, slow. The slow process in which all the states through which the process passes. You remember in the PV diagram all those process. It has to be all those process are happening at a very slow rate, and each of the process are in equilibrium. Okay, so almost a slow process is called a quasi-static process, and all those states involving in that process are in equilibrium, thermodynamic equilibrium. Okay, so if it is a quasi-static process, let's say this is 1 and this is 2, we show it using the path. Okay, these are the in-between process, in-between states. So we use this curve like thing for, or you can say joint line. Okay, means we have joined all the dots representing all the states, and 1 and 2 represents the initial and the final state. So joint line represents a quasi-static. So this is quasi-static, and obviously it's in slow. All the states are changing in slow manner. And if it is not a non-quasi-static, non-quasi-static, then what happens? Your state 1 and state 2 and all the process in between will be shown in a dotted line. Okay, it means non-quasi means it's a fast process, and quasi means it's a slow process. Okay, and this one is fast. Okay, so to understand this, we can get this piston cylinder arrangement, whereas the piston is given a weight. Let's say each are 5 grams. Okay, and we are removing one dead weight after another. Then, or you can say, wow, we are putting one dead after another. Then it will show the piston will move in a very slow manner, right? So this kind of arrangement we can say represents your quasi-static process. So all reversible process are quasi-static process, but vice versa, the opposite of it, all quasi-static processes are not reversible process, means the vice versa is not true. So let me repeat, all reversible process are quasi-static process, but all quasi-static process are not reversible process. So we can understand this piston cylinder arrangement where we are giving stopper weights or dead weights of 5 gram each. Total it's 20 grams. Okay, let's say 20 gram. But if we go on adding or removing, depending on where the piston is moving up or moving down when we are adding it, and this kind of processes that we are realizing with this example is a very slow process, and by this we are trying to understand the quasi-static process. So I hope you have understood the reversible process, irreversible process, and this quasi-static process in this video. In the next lecture we'll be coming up with the next topic. Till then, take care. Bye bye.